hope we have convinced you of the importance of the role of algorithms in programming, and specifically in the efficiency of your programs. But what if you've settled on what you believe to be the ideal overall algorithm for your problem, and yet your implementation is still too slow for your purposes? Is there anything more you can do to improve it? Many times the answer is yes. The reason for that is that there are many different ways to implement the same algorithm, and implementation can make a big difference. All programming languages come with built-in operators and built-in functions. Deciding which ones to use and how to combine them while coding a particular algorithm can have a profound effect on the speed of your program. And decisions on implementation are especially important in MATLAB, which was invented expressly to work with matrices and arrays. The inventor, Cleve Moeller, was, and still is, an expert in the field of numerical computation, and he was using the notation of that field every day when it occurred to him that there should be a computer language that incorporated that notation. The notation of numerical computing included operations like matrix multiplication and matrix transposition, each symbolized by a single operator, with all the looping and indexing required to carry out those operations implied but not written out on the page. Moeller's decision some 40 years ago to incorporate those operators directly in MATLAB forced him to incorporate the same implicit looping in the language itself, and it has had a huge impact on numerical programming. The most obvious example of implicit looping in MATLAB is the matrix multiplication operator, in which one asterisk takes the place of 3 nested for loops, 3 index variables, 8 indices, and scalar multiplication and addition operators that are required in our matmul function, for example. But matrix multiplication is just the beginning. Implicit looping is everywhere in MATLAB, with all its other arithmetic and logical operators and the hundreds of built-in functions that handle array inputs and outputs. What all this implicit looping means is that a simple MATLAB command like adding, subtracting, multiplying, or even dividing 2 matrices does not require even one explicit for loop, or while loop, or include even one index variable. Looping still happens under the hood, but you can avoid all the programming time required to make it happen. And furthermore, it's implemented by highly optimized low-level libraries of functions that are extremely fast. As a result, many slow MATLAB functions can be changed into fast functions by replacing explicit loops with operations or functions that operate on entire arrays via implicit loops. A function or an operator that performs matrix multiplication, or any function that operates on an entire vector or an entire array, is said to be a vector command. And the translation of code from a version that uses explicit looping into one that uses implicit looping via a vector command is called vectorization. In every case of vectorization, at least one explicit loop is avoided. And you should strive to avoid explicit loops if there's any way to accomplish the same thing with vectorization. If you're new to programming and MATLAB is your first language, then you are in good shape. But pity the people who, like I did, come from a traditional programming language like C, C++, or Java that lack the built-in support for vectorization that MATLAB has. Even when they have the power of implicit looping at their fingertips, they have a strong tendency to stick with explicit loops because that's what they're used to. If you come from that tradition, and even if you don't, I recommend strongly that you make a conscious effort anytime you're implementing a computationally intensive algorithm to try to avoid explicit loops, and think of ways in which you can solve your problem with vector commands instead. As you will see, it can result in dramatic speed-ups of your program, and in many cases you'll get code that's less prone to error and easier to debug in the bargain. Remember the routing example from our previous lecture? We wrote 3 versions of it, and our last version was 200 times faster than our first naive attempt. Here's version 3 again. You'll remember that our analysis showed that we were doing lots of unnecessary work in versions 1 and 2, which we eliminated by pre-calculating this RW vector, saving a calculation here in X, and then reusing these values instead of recalculating them. This sophisticated approach to the problem resulted in an inner loop in which all we did was a single multiplication. Let's time version 3 once again. Don't worry, I won't make you wait. Yeah, it's sophisticated all right, but there's another approach that's even sophisticateder than that. Nthroot calculates the root of the first argument that's specified by the second argument, and that's how we've been using it. But if you check the documentation for Nthroot, you'll see that like most numerical functions, it also allows vector input. You can give it two vectors of the same length as inputs, and it'll loop through them, finding the root of each element of the first argument that's specified by the corresponding element of the second argument. So if we give the entire vector w as its first argument, and the vector of indices of w as the second argument, Nthroot will return all the roots we need for w in one function call. And we can do the same thing to get all the roots we need for v in one function call, like this. Note also that we no longer need to allocate space for RW to make the explicit looping more efficient, because we got rid of the explicit loop that calculates RW. Let's time version 4. Well, that didn't help a lot. You know why? That's because we're not working on the part of the code that's taking most of the time. The number of operations that these two commands take is proportional to the length n of the inputs. The number of operations in the nested loop is proportional to n squared. That's where most of the time is spent. Let's see if the profiler backs me up on that. I'll run it on version 3. Okay, the profiler shows that all the Nthroot calculations took only 2% plus 0.8%, 2.8 total percent of the time. Friends, we're barking up the wrong tree. We're off the track. We're in the woods. This dog won't hunt. Here's where we're burning up the silicon. And these two lines, 10 and 11, which constitute the nested loop of multiplications. Yep, the profiler backs me up on that. So, since our latest improvements didn't accomplish much, are we done? Is that all she wrote? The end of the line? Our last hurrah? No, not a bit of it. We're not done yet, folks. You might have noticed that the computation happening in the nested loop here could be done with matrix multiplication instead of a nested loop. If you did, then go to the head of the class. That's the sort of thing that it takes a lot of experience to spot. What we're doing in this loop, in this nested loop, is equivalent to multiplying a column vector of the values of RV times a row vector of the values in RW. And that's the same as multiplying an n by 1 matrix times a 1 by n matrix. And those dimensions are compatible for matrix multiplication. And not because of the n's, but because of the 1's. The inner dimensions are both 1, n by 1, 1 by n. So we can do that with the built-in matrix multiplier in one operation, with implicit looping hidden deep inside. Here's version 5, which does exactly that. Right here. I should add that to get a column vector RV, which was a row vector from Nthroot, we have to transpose it. So we're actually using two matrix operations, transposition and multiplication. So with 4 vector commands, we have completely vectorized the code in this function. And with that change, we have swept every trace of every index and every subscript out of our code. Now, isn't that the sophisticatedest darn thing you've seen in a long time? I mean, look at how simple this is compared to, say, version 3. Such sleek styling, such smooth lines, such a low profile. Let's take this little beauty out on the track and see what it can do, shall we? .2050. Man, this thing lapped V4 almost 7 times. This thing is not only beautiful, but it's fast. We've vectorized the calculation of the roots of V. We've vectorized the calculations of the roots of W. And most importantly, we've vectorized the product of the roots to get A. And while this thing is cooling down, I want to emphasize that vectorization not only makes it fast, but it also makes it beautiful. And lest you think I've been at the keyboard too long, I mean it's beautiful to a MATLAB programmer because it's simpler and easier to understand, and as a result, it's less likely to have errors hiding in it. Maybe an II that should be a JJ or vice versa. Oh, maybe I should check that. Perfecto. And one last comment about what the program looks like. When I look at V5, it seems much more straightforward than V3 or V4. That's because I'm so familiar with matrix multiplication in MATLAB. But to a MATLAB newcomer, that may not be true. It certainly was not true for me 25 or 30 years ago when I first encountered MATLAB after having programmed for over 20 years. The loop approach at first seemed much more straightforward than, say, RV prime times RW. But that's just a function of experience. If you are learning programming and MATLAB at the same time, then you will not suffer from bias toward either approach. You are a lucky person. And back to the improvement from V4 to V5. We haven't changed our algorithm. We haven't avoided any additional work by storing additional results. And we haven't taken advantage of the characteristics of input to avoid calculations, the things that we were talking about in our last lecture. In fact, we don't even pre-allocate. We're doing all the work and all the calculations we were doing before with exactly the same set of arithmetic operations, and the order of our algorithm is still n squared. The only difference is that we're doing it all faster. Well, we're actually not doing anything. The computer is doing it, and the speed up comes from the fact that MATLAB's operators and built-in functions are highly optimized, use specific hardware features, and are just plain blisteringly fast. The evolution of our simple rooting example from version 1 all the way to version 5 is an example of the art of programming. Our first solution, which was a perfectly reasonable attempt, would take over 12 minutes to do the same calculation that our 5th version did in about 1/5 of a second. With some thought and a little work, we improved the performance by a factor of 4,000. Even though the time complexity of all 5 versions of our function was exactly the same. And I'll stand behind this statement. Our artwork has led to something beautiful. Again, and I cannot stress it enough, force yourself at every opportunity to use built-in operators, built-in functions, whenever you can. Your code will run faster, and as a bonus, will be simpler, easier to read, easier to debug, and less prone to error than if you stick to explicit loops. As I mentioned, developing efficient programs is an art. It takes experience to develop the skill and intuition that can lead seasoned programmers to see solutions that others might miss. In fact, a major stumbling block for MATLAB beginners is that it's often not obvious that a vectorized solution to the problem they're working on is even possible. That matrix multiplication trick that we pulled out for routing version 5, well, it's an example that'll pop out to experienced MATLABers, but it's unlikely to occur to a wet behind-the-ears beginner. Some tricks take advantage of logical indexing, and we provide a thorough introduction to logical indexing both in our textbook and in our first course. We haven't done any time comparisons or profiling of it for you. Let's do that now. And I've got a surprise in store for you. Here's a task that can be solved in one line with logical indexing. The task is to take an existing matrix and set to 0 every element of it that's smaller than some limit. Let's start with a nested loop solution. It's called small to 0 version 1. And let's time it on a big matrix. Not too shabby for 100 million elements. And now let's time a solution that uses logical indexing. This is version 2. Put it down here so you can see both of them at the same time. This one-liner could be used without defining a function, but we're going to compare the two implementations, so we want to be fair and include the function calling overhead. So let's time this one and admire its speed. Almost twice as fast. That's pretty good, but is that all we get from the low-level processing that exploits the hardware to the fullest and all that blistering speed and stuff? Maybe most of the time was taken up in function calling and adding a workspace to the stack and all that stuff, the stuff we talked about in Lesson 2. Let's time it as a command in the command window. I use tick-tock because time it won't work for this example. That's because time it requires an anonymous function, and you can't put assignment statements in anonymous functions. Only expressions are allowed. But getting rid of the function overhead did reduce the time by over a factor of 3. That's something to consider whenever you're calling a fast function, but are calling it so many times in a loop that the overall speed of the loop is too slow. If that fast function isn't too complicated, then instead of calling the function, you can just put its body into the body of the loop, being careful when you do to use unique variable names, and you'll get a speed up with no change in the algorithm. Okay, so the version with implicit looping is almost 7 times faster than the version with explicit looping. That's a big speed up, but it's not surprising. So where is the surprise I told you about? Well, it's coming. Let's profile this first version of the function, which took just under 1.5 seconds. That's taking a lot longer than 1.5 seconds. Let's look at the profile. "15.5 seconds. What's going on? So the if statement takes 7.6 seconds, and the loop indexing, which is always charged to the end statements of the loops, it's taking 3.7 plus 3, another 7 point something seconds. So why did this function slow down when we profiled it? I know there's some overhead to profiling, but that can't explain a factor of, 10 slowdown. Well, here's the thing about the profiler, and here comes the surprise. It turns off MATLAB's code optimizer. What's that? You didn't know that MATLAB optimizes your code? Well, it does, and that's the surprise. First off, the code that MATLAB runs is not the code that you write. That's never true, because when you tell MATLAB to run a function, it translates the code into something that can be executed by your computer's processor. MATLAB looks at the whole file and translates it into a form that takes advantage of the processor hardware, and that translated code is what actually runs. This translation step is called just-in-time compiling, and it includes optimizations. Those optimizations are guaranteed not to change the results, but the order of some operations might change, and the looping may be optimized almost as much as implicit looping in the vectorized code. The result's never likely to be as good as the vectorized version, but it gets better every year as the engineers at the MathWorks keep improving that compiler. If you want to know more about the optimization methods it uses, well, join the club. Those methods seem to be top secret proprietary information at the MathWorks. And their attitude about it is that programmers should not be adjusting their code to take advantage of the optimizations anyway, because those optimizations may change. So it's best they keep the details secret. And one last thing about just-in-time compiling. When that compiler translates the code for a function, it saves the translation into an internal file, so that until you edit the function or restart MATLAB, it doesn't have to translate it again. For this reason, the first timing of a function's execution after editing it or after restarting MATLAB tends to be noticeably longer than subsequent timings because of the just-in-time translation step. And if you clear the function by giving the clear command with the name of the function, or give the command clear all, MATLAB deletes the translation. So unless you need to clear it, like say to reset a persistent variable, it's best not to. So you can't use the profiler to compare vectorized code with optimized code times. That might take some of the sting out of not having it in MATLAB Online, as a matter of fact. But the profiler is still useful for reinforcing your ideas about where your code is spending most of its time, if not for providing reliable exact time ratios. Now let's look at another problem. Set every element of the array A to 0 that's smaller than, say, the second element in its own row. For that problem, it might seem that a nested loop solution is the only option. Say like this. The nested loops iterate through all the elements of A, and then the if statement checks each element against the element on the same row in the second column and sets it to 0 if it's smaller. I'll let you check to see if it's correct, but I show you this example because it's not at all obvious how you would vectorize it. Well, it's time to trot out the built-in function named repmat. Repmat stands for replicating matrices, and repmat makes its living by making copies of vectors and arrays. It's helpful in situations like this, where it's necessary to compare every element in a matrix to elements in one column of the matrix, or of another matrix, or to elements in one row, or in some rectangular subset of a matrix. Let's start by getting a random matrix to work with. And now let's call repmat. The first argument tells repmat what you want it to replicate, and in this case we're giving it the second column of A. This is the tile, and repmat will take this tile and lay out copies of it according to the next two arguments. In this case, those arguments are 1 and 5. And they tell repmat how many tiles to lay out vertically and horizontally. So repmat takes the second column of A and replicates it one time in the vertical dimension and 5 times in the horizontal dimension. The result is a new matrix that has the same size as A, and each row consists of the same element, which is the corresponding element of the second column of A. Once we have this matrix, we can use it with logical indexing, like this. Voila! A single line instead of a nested loop structure. I'll admit it's not really all that beautiful, but it's got the loop version beat. And what we've done is compare every element of A to the corresponding element in this tiled version. And if it's less than the corresponding element, we set it to 0. While we're on the subject of logicals, let's look at find again. It helps you search in vectors and matrices. And as we mentioned, instead of searching for values that you give it, it looks for non-zero values. When it finds them, it returns a list of their indices. And you can add a second argument to tell how many to return if you don't want them all. At first, it may seem strange that it looks only for non-zero values. I still remember thinking that this was a pretty stupid idea those many years ago when I was a beginner with MATLAB, because if I'm looking for certain values, what good is it to return non-zero elements? Well, the stoop turned out to be me, because it's very good if you combine it with logical arrays. The result can be a very powerful and versatile search that avoids lots of messing with explicit loops. Let's cook up a command that will locate the indices of odd elements in a vector of integers. Our recipe calls for 3 ingredients: the function find, the function mod, and a logical array. First, let's refresh our memories about how mod works by looking at some examples. So here we have mod of 7 and 2. If you divide 2 into 7, you get a remainder of 1. If you divide 2 into 8, you get a remainder of 0. 3 into 12, you get a remainder of 0. 7 into 48, remainder of 6. It's similar to the rem function, which also calculates remainders, and you can look them up to see what the difference is between the two. So, in summary, you give it 2 arguments, and it gives you the remainder when the first argument is divided by the second argument. The first argument can be a vector, and it works for any real numbers. But we'll stick with integers, and we're interested in odd integers. So we just note that dividing by 2 gives 1 for odd integers and gives 0 for even integers. Let's get a vector of integers to work with. Now let's get a vector of 1s and 0s for the odd and even values in V. Here we've used mod, and this time our first argument is a vector. Since 81 is odd, we divide by 2, the remainder of 1. 90 gives a remainder of 0, and so on. And now let's get a logical array that's true for non-zero entries and false for 0 entries. Here we're setting true-false equal to the expression 1 zeros is equal to 1. That's true in the first case, so we get logical 1, false in the second case, logical 0 for false, and so on. And finally, let's search for non-zero values in this logical array. And we find them at index 1, 3, 4, 5, 8, and 9. And that makes sense because if we look back at V, we see in position 1, 3, 4, 5, 8, and 9 that we have odd integers and all the rest are even. And now that we know how to use all these ingredients, we can mix them together and get our command. There we have a single command. Inside, we take the mod of V2. That gives us 1s and 0s for odds and evens. We use that in the expression mod V2 equals 1, which gives us true and false. find finds the trues, that is the non-zeros, and reports them to us, and we get the same result in one command. So you've seen how find can return the indices of non-zero elements in a vector. But find can give you row and column indices for two-dimensional arrays too. Let's form a 3 by 4 array of integers. And let's find the odds. Nothing showed up in the command window because I suppressed it with the semicolon. But you can see from the syntax that to get rows and columns, you just give two output arguments. Now let's look at these rows and columns this way. So I put row, comma, column. That makes an array. Row, column, row, column, row, column. And that tells you that in the array A, at element 1, 1, we have an odd number. At element 3, 1, an odd number. At element 1, 2, an odd number, and so on, all the way to 3, 4, which is odd. And of course the rest are even. You may have noticed that we'd have gotten the same result if we'd just given mod A2 to find instead of mod A2 equals 1. But this does not work in the general case when we're searching for numbers that are divisible by some given number, or negative numbers, or more elaborate conditions. For those cases, you must use a logical expression, so we used one here to give you the idea. If you wanted to find evens, for example, we would use the same logical expression, except we would change the 1 to a 0. So with the help of logical expressions, find can find what you want to find, and it can find it in vectors and arrays. But you won't find any explicit loops in a call to find. Well, believe it or not, as long-winded as I can be, that last sentence with its 6 finds wraps up our treatment of vectorization. We haven't made you an expert, but you should have gotten that concept by now, and that was our goal. But I've got some wind left, and this lecture is not over yet. Beyond vectorization, we've got a few other tricks up our sleeves that can help to speed up your algorithm. Now begins the other speed up section of this lecture from the title slide. First stop, recursion. Or rather, first stop recursion, as in stop using it. While recursion is an elegant way to solve many problems, it can come with a performance penalty. As we illustrated using the factorial problem, most of the time an iterative solution will be faster. A function call takes time, so if a particular problem takes 1,000 iterations in a for loop, or 1,000 recursive function calls, the latter will be slower, probably much slower. And as we saw with our fact a couple of lessons ago, we can also run out of stack memory if we make too many recursive calls. Recursion can give you a solution to some problems for which an iterative solution is more difficult to see, like visiting all the folders in a subfolder tree, or sorting lists, or that binary search we studied. But if after programming a recursive solution you find that recursion is taking too much time, after you've done all you can to speed it up, well, it's time to work out an iterative solution. It's almost guaranteed to go much faster. As we explained in the first course, when MATLAB calls a function, the model for passing input arguments is call by value, meaning that a copy is made on the stack and the function accesses the copy as a local variable. The point is that any changes made to that local variable by the called function will leave the actual argument in the caller unchanged. If we pass a large array as an input argument, it would take a long time and lots of memory to copy it onto the stack. But MATLAB has a trick up its sleeve to save time when it can. When the function is called, MATLAB copies only a pointer to each argument onto the stack to begin with. This method of passing an argument is termed call by reference. If the argument is a large array, then call by reference represents a big savings in time. However, MATLAB then watches that function like a hawk throughout its execution And if it ever starts to change so much as one bit of that argument, even if it's just one element of a 100 million element array, MATLAB pauses execution, copies the entire array onto the stack then and there, and then continues execution. At that point, call by reference is abandoned for that variable, and MATLAB switches to call by value, which is a fancy way of saying that the argument is copied onto the stack. Therefore, unless it's absolutely necessary, you should avoid changing elements of potentially large input arguments in any functions. Let's see an example. It's a trivial function that just returns the maximum value of its argument. Let's run it. First, we'll set up a big array. And we'll hand it to time it. And it takes 0.15 seconds. Now let's make a trivial modification. We change one element and run the code again. It took over 10 times longer. And all that extra time was spent making a copy of this array instead of passing it by reference because of this one change in the called function. So keep this in mind when you work with large arrays and pass them to functions. And one last comment about avoiding needless copying of the input arguments. Do you remember in our third lecture of this lesson when we looked at binary search? Well, we declared that its time complexity was order log n. And that's true. But it's true only because of call by reference. Since the binary search function doesn't change its input argument, the list that is passed in is passed by reference. If the list were copied in a call by value, that would require n copy operations for a length n list, and the function would have been order n. The next item on our list of other speedups is index reordering. When setting up a nested loop to process the elements of a matrix, we typically iterate over the first index in the first or outer loop and iterate over the second index in the second or inner loop. Well, there are good reasons to change that order. Like this. Or this. One reason has to do with array reallocation. We've recommended that you pre-allocate arrays whenever possible, and we stand by that now. But there are some situations in which pre-allocation is not possible, because the function can't know what the ultimate size of an array will be until it's done writing data into it. If the array is big, then the lack of pre-allocation can slow things way down, as we saw in the previous lecture when we commented out the pre-allocation of an array and the runtime ballooned from a mere 1.5 second sprint to a disastrous 400-second slow walk. But even when pre-allocation is not possible, there is sometimes a way to avoid total disaster. Take a look at this example, which comes from Chapter 2, Section 4.9 of the 3rd edition of our textbook. This function produces a matrix whose row size is determined by its input argument, but its column size depends on the numbers that happen to come out of a random number generator, so its size can't be known in advance. The use of the random number generator to make it unknown is done here only for the sake of illustrating the issue with a simple example. In general, it might be unknown for some other reason, but in any case, as a result of its ultimate size being unknown, pre-allocation is not feasible. So A must be reallocated every time the outer loop iterates and a new row is needed. Let's time it. Okay, that's definitely slow. So what to do? Well, one solution is to allocate a matrix of a size that's larger than the expected size required, and then trim it down to the actual size if necessary, or let it grow in the loop. But we want to introduce the idea of reordering the indexing, and that can solve the problem too. Let's look at an implementation that does that. The difference is that in this version, the indices of A are swapped from IIJJ to JJII, as we just showed, so that the inner loop increments the column index instead of the row index. When the inner loop is done with its column, the outer loop increments the row index, which shifts us one column to the right, and then the inner loop starts adding elements of that column below the previous column. To summarize, each iteration of the inner loop adds an element of the current column below the previous element, and each iteration of the outer loop adds a column below the previous column. As a result, a new column is added for each iteration of the outer loop instead of a new row. Of course, these loops end up calculating the transpose of the matrix we want, so A must be transposed after the looping is done. That transposition requires time too, but it's a single operation that's implemented with low-level processing that's so fast that we can neglect it. So all we're doing here is assigning values to the elements of A in a different order. But what a difference the order makes. Almost 100 times faster. Now let's check the results to make sure they're correct. Yeah. So why the big speed up? Well, to see what happened, we need to remember that an array is not arranged in 2 dimensions in the memory. It's laid out in linear form, in column major order, meaning that the first column is laid out first, followed by the second column, followed by the third, and so forth. So in our second version of not pre-allocatable, when we need to add a column, column II, that new column goes at the end of the current matrix. The just-in-time compiler is likely to leave that space open, so that column can be written there and the rest of the array stays where it is. To make that a bit clearer, let's consider what happens after the second column is completed, as we do in the textbook where this example came from. At this point, the array is laid out in the memory like this, where n equals 3000 and the blue line shows the consecutive ordering in the memory. In other words, the 2-column array is laid out in consecutive memory locations in this order. Now we're ready to add element 1, 3. Let's see where it goes. A 3-column array is laid out like this. In other words, the 3-column array is laid out in consecutive memory locations in this order, where the red type indicates the places where new elements must be inserted. So, the new elements can be added without disturbing the elements that have already been stored. But now think about that first version. Let's consider what happens after, say, the second row is completed. At this point, the array is laid out in memory like this. In other words, the elements of the 2-row array are laid out in consecutive memory locations in this order. Now we're ready to add element 3, 1, the first element on the 3rd row. Well, where does it go? To see where it belongs, we need to look at the layout of an array with 3 rows. An array with 3 rows is laid out like this. In other words, the 3-row array is laid out in consecutive memory locations in this order, where the red type indicates places where new elements should be inserted somehow between the existing elements of the 2-row array. Unfortunately, such insertions are impossible because there is no room between the consecutive memory locations. Instead, space must be reallocated for the array. To do that, it's necessary to set aside enough room for a new 3 by 3000 array and then copy all 6000 elements of the existing 2 by 3000 array into the new array. Only after all that's done can the newly calculated first element on the 3rd row be written into its appropriate position, followed by the other 2,999 elements on that 3rd row. This reallocation process must be repeated for each iteration of the outer loop, except the first. And how many times did that reallocation happen in our case? Well, it's one less than the column length, which is, let's see, 4,211 times. That's a lot of unnecessary work, and we avoided it all in version 2. Okay, this is the perfect time to let you in on a valuable secret. And that secret is as follows. In general, any pair of nested loops is likely to run faster if the inner loop increments the column index instead of the row index, whether or not you can pre-allocate the matrix. The key difference is that a loop that increments the column index steps forward in the memory one element at a time, while a loop that increments the row index steps forward an entire column at a time, which for an m by n matrix is n elements per step. The step distance is called the stride, so that's an n element stride. And stride 1 steps are handled more quickly by the CPU. Incrementing the column index in the inner loop gives column major order, and incrementing the row index gives row major order. And column major order is faster. Here's an illustrative function that allows you to write either order with or without pre-allocation when assigning values to a matrix. The first two arguments are the column and row lengths, and the third and fourth arguments determine whether or not column major order is used and whether or not pre-allocation is used. The body of the function provides a column major versus row major option by means of the choice of two different nested loops. And it puts the row major order in second place because, frankly, it's not a gold medal winner. However, and this is the point of showing you this code, you can see that row major order is the more natural way to program nested loops because it's more natural to write the indices that specify an element of the array, iijj, in the same order as they appear in the loop control statements, iijj. On the other hand, to go for the gold up here in the column major approach, you have to put the indices that specify the element of the array in the order jjii, opposite to the order iijj in the loop control statements. And you have to swap the limits m and n too. But that's all it takes to achieve stride 1 access to A, and that's all it takes to win the gold. Not quite as rigorous as, say, I don't know, Olympic training camp. So let's test my claim that column major order is faster even when reallocation is not an issue. Let's run this example both ways and time it on a 10,000 by 20,000 array. Okay, in this first call, I set the third and fourth arguments to false and true to give row major order and get pre-allocation. Now to get column major order by changing that third argument to true. And column major wins the gold with a time better than row major by a factor of 3, and the crowd goes wild. Well, at least I'm pretty sure they'd go wild if a race were won by a factor of even 2. From what I've seen, an Olympic crowd can go into a frenzy over 1/100th of a second. By the way, not many people know that I've had my own Olympic aspirations, but I've been thwarted in that for years by the limited thinking of the Olympic Committee, who cannot seem to accept keyboarding as an Olympic event. I mean, they've got curling, so, anyway. Making big strides sounds in general like a good thing in life, but in inner loops, it's the pits, because as we've seen, it slows looping down. But the irony is that most people do it that way. My gosh, is there no end to the irony in this lesson? So why is the more natural way the less efficient way? Well, it's the result of an unfortunate language design decision made over 60 years ago that we're still living with today. It happened on that fateful day in 1954 when the designers of Fortran, the first high-level language for numerical computing, decided to map the order of array elements in the memory onto column major order in the language. so the stride 1 index is the first one instead of the last one. It's unfortunate because, as our example shows, when programmers write nested loops, they're naturally prone to iterate over the first index in the first loop, the second index in the second loop, and so on. And as a result, the stride in the innermost loop, instead of being 1, is as large as possible. MATLAB followed the Fortran lead probably because programmers moving from Fortran to MATLAB expected it to be that way. Other languages like C and C++ use row major order. But programmers in the know the order of their language and take advantage of it. But hey, now you're in the know too. You know that for maximum speed, the MATLAB loop that advances the first index of an array should be the most deeply nested one. So you can do that too and produce faster code. If you program in MATLAB for a living, that means you'll make a better living. It's like I said, this is a valuable secret. I've let you in on it because I like you. But the fewer other people that know about it, the more valuable it is. So maybe let's just keep this one on the down low. So we've given you lots of methods to speed up your algorithms. And every speed up had to do with a loop. Frankly, that's because loops are the only things worth speeding up, whether they're for loops or while loops. That's where algorithms spend almost all their time. But guess what? There's one more kind of loop in MATLAB, and we're going to finish with that. It's called par4, spelled P-A-R-F-O-R, and it stands for parallel for loop. Considering its meaning, I guess it might be more consistent to pronounce it par4. Nobody does that. Par4 was introduced into MATLAB in 2012, and it's available only if you have the Parallel Computing Toolbox installed. What par4 does is run iterations of its body in parallel, that is, simultaneously on separate CPU cores, if, that is, your computer has multiple CPU cores. These days, modern CPUs almost always have multiple cores, and par4 can take advantage of them. There is one restriction, though. The body of the loop cannot depend on earlier iterations of the same loop. That is, par4 works only if the loop body can be executed in any order with no effect on the outcome. For example, remember our slow vector flipper function called myFlip? Can we speed it up by throwing more cores at it? Nope, not happening, because an iteration of the outer loop depends on the previous loops having already flipped the elements from index 1 to index II. The inner loop also must be executed in order. If not, we would overwrite elements of the list before they were copied to a new place. So both of these loops must be executed in the same order, and therefore neither loop can benefit from par4. And there's an issue of practicality, which is that par4 makes sense only if the body of the loop is slow enough to make up for the extra time required by par4 for the overhead of dividing up the work across multiple cores, sending them the data they need to work on, and then collecting the results. So a par4 version of an iteration can be slower than a regular for loop. But in scientific computing, the body of a for loop is often very slow because it does a large number of complicated computations. And a very common situation is that we need to perform these computations repeatedly on random or otherwise independent data so that we can compute statistics on their outputs. Such testing, in which a problem is solved repeatedly on randomly generated data, is a perfect opportunity for parallel processing, because each repetition is totally independent of all other repetitions, so the order is unimportant. To show how it works, let's try an example similar to what we're showing here in our schematic, which is a modification of a MATLAB example in the documentation for par4. We'll start with a for loop version first, and then switch to par4 with the same loop body. Our for loop version is called eigen4, and it computes the eigenvalues of a set of matrices stored in a three-dimensional array named A3D. Eigenvalues are an important concept in linear algebra, and calculating an eigenvalue is computationally intensive. And we've got a par4 version ready right here. The only difference between this function, which is named eigenpar4, and eigen4, is that the keyword 4 has been replaced by the keyword par4 in this one. I'm going to time both of them on the same array. And since they're a bit slow and the exact timing is not that important, I'll use tick-tock again. First, let's get a big array to test on. So we're going to calculate the eigenvalues for 50,000 matrices of size 50 by 50. Let's start with the for loop version. As usual, I cut out a lot of waiting time for you. Now, before we run par4, I want to do something first, and that's to command MATLAB to prepare CPU cores for par4 to run on. We do that by clicking on these little gray bars down here. If you don't see them in your version, then that means that your system doesn't have the parallel computing toolbox installed. But that's okay. You can get your thrills watching me use it. You know, like watching other people play soccer. So we choose Start Parallel Pool, and a little yellow box shows up with a reassuring message, and the parallel bars turn blue and start pulsating, meaning that things are being gotten ready. This preparation is necessary before par4 can run. It would happen automatically if we ran eigenpar4, but it takes a while, and I don't want preparation time to be included in the tick-tock time, because it doesn't need to be done every time you use par4. MATLAB calls the process that handles the loops assigned to a particular CPU core a worker, and calls the set of processes for those cores a pool of workers. Once this pool of workers is ready, they stay ready until they time out or we shut the pool down. And since we typically run functions many times, what we really want to know is how fast the par4 version runs when everything's already set up. Otherwise, it would be like including the time it takes to put on running shoes in a 100-meter dash. Okay, they've stopped pulsing, so par4 has got its shoes on. Let's see how fast it can run. So with 4 cores, we gained roughly a factor of 3 speed up. Each core performs about 1/4 of the iterations. They're all working at the same time, so you might expect a factor of 4 speed up. But actually a factor of 3 is reasonable. Theoretically 4 is the maximum, of course, but because of the overhead we discussed a few minutes ago, 3 is probably the best we can reasonably hope for in most cases when using 4 cores. And did we get the same answer? Yes, we did. But that's how easy it is to do parallel processing with MATLAB. If you are a person who needs to speed up a slow loop that has independent iterations, and you are also a person who has MATLAB installed on a computer whose processor has multiple cores, and you finally are a person who also has MATLAB's parallel computing toolbox installed, then you are a candidate for parallel processing. Of course, the intersection of all these 3 sets of people is relatively small, and it omits all of you who are using MATLAB online, because as of now, in the summer of 2020, MATLAB Online doesn't support it. So we're not going to spend any more time on par4. We've omitted lots of details, of course, but what we've shown you is all you need to get started. If you are among the lucky few who have access to it, then we recommend that you read the documentation because those details can help you improve your results. An example is that you might get an even greater speed up if you use the multiple threads option, which allows the cores to share memory and so reduces communication times. You do that with the parpool function. But the threads option doesn't work for all loop bodies. Like I said, you need to read the documentation to get the most out of parallel processing. And with that brief look at Par 4, we have reached the end of this lecture and the end of Lesson 4. In this lesson, we focused on writing efficient code, meaning specifically code that runs as fast as possible. Of course, the code must get the right answer, but there are many ways to get that answer, including via multiple algorithms, which we discussed in the first 3 lectures, culminating in their categorization via the concept of algorithmic complexity. In our 4th lecture, we suggested ways to speed up an algorithm by eliminating unnecessary work and taking advantage of the characteristics of the input. And in this 5th and final lecture, we focused on methods to speed up the work that can't be eliminated by means of vectorization, logical indexing, avoiding function calls, call by reference, reduction of array reallocation, efficient index ordering, and finally, parallel programming. We hope that this study of efficiency might provide you with a framework to help you analyze the algorithms you choose and the implementations you use when you solve problems with MATLAB code, and that it will help you produce code that's faster with fewer bugs, and finally, that it'll prove useful in your future computing endeavors.